Good afternoon, everyone. My name is Peter Esselman. I'm a research fish biologist at the USGS Great Lakes Science Center in Ann Arbor, and today I'm presenting work that I've been doing with Chuck Medengen, also from USGS. USGS is committed to provide the best possible information about prey fish abundances to our fisheries management partners in the Great Lakes. And when we identify weaknesses in our assessments, we're also committed to develop new methods and apply those methods to come up with better estimates. Toward this end, we've been investing in new methods to assess round goby abundances using emerging technologies like the autonomous underwater vehicle that you can see here. Today, I'll be presenting some work where we're using AUVs to develop a new whole lake index of round goby abundances. Round goby are an important prey item for lake trout, walleye, yellow perch, lake whitefish, and other predators in the Great Lakes. For instance, on the bottom right, you can see the orange bars represent round goby diet proportion by wet weight in different statistical districts of Lake Huron in 2017 and 2018. You can see a clear pattern of dominance by round goby in the guts of these lake trouts. The USGS bottom trawl is assumed to provide goby estimates that are biased low. In other words, we underestimate round gobies. And the reason for that is that the large vessels that we use to sample don't do a good job sampling the shallow habitats where gobies are distributed. And they also don't sample the rocky habitats where round gobies are known to occur at higher densities. We've been developing a new robotic image acquisition system that has been tested and is now ready for full-scale deployment. And we've also been working on software and custom software to automate the processing of the large amounts of data that come off of the robot. GobyBot is an autonomous underwater vehicle, which is an untethered vehicle that you give a pre-programmed track, and then you release it into the lake, and it basically conducts your mission and comes back to the surface and is retrieved. This particular robot has an object avoidance sounder to help it avoid collisions in the front. It has a 10-inch section that has a sophisticated gyroscope that helps it track its position underwater in currents and upwellings. And it carries two camera systems. One is a color camera in the rear, and one is a lower resolution grayscale stereo camera. You can see that the AUV can travel to 200 meters depth, which is well beyond the maximum depth where round goby are being found in the lakes. You can see here the AUV being recovered in a small vessel operation. It's essentially released and recovered by small vessels. It's pretty heavy to get over the side, but a couple workers can handle it, and so we operate with two-person crews most of the time with our AUV operations. When the AUV is underwater, it's essentially tracking the bottom with an altimeter. You can see here behind the orange mask the two camera sections that are basically taking 5 frames per second along the lake bed for up to 10 kilometers at a time, hours at a time. This is the type of image that we get from the AUV. If you look carefully, you'll see a number of benthic fish present in this image. And those fish can be traced or identified in different ways. And the process we use, essentially starting here in the upper left, is we take our raw imagery, we screen them to make sure that they're usable, i.e. there's good exposure, there's not turbidity. And then we trace the gobies, and this can be done by hand or by machine. And then we apply an automated process to estimate the length of the gobies, which gives us both the size of them as well as the number of them in each image. And then those data are tabulated. Using the field of view of the camera, we can calculate the area of each picture, which allows us to calculate either the number or the weight per meter squared, which is a density estimate. And then by averaging over many photographs, we're in a position to summarize goby abundances. In 2020, we went out to Lake Michigan and we collected data at 30 10-kilometer sites. The red dots here show sites where we inferred that there was coarse substrate, and the blue sites show places where we believe there's fine substrate. We stratified our sample this way because we know that gobies are more abundant in coarse substrate. You can see the blue line here represents the 30-meter depth line in the lake, which essentially is the lower limit of goby summer distribution. Over the course of our survey, we sampled hundreds of thousands of images, and when we subsampled every 25th of those, we had 100,000 images. Then we had a team of people look at each image and classify them as usable and unusable, and those data are shown here on the right. The green part of the pie chart shows the proportion of each collect that was usable, and the dark numbers show the number of images that we're interpreting for each site. Places like the Door Peninsula, where we didn't have a lot of usable data, were largely affected by turbidity, and in other locations we were affected by overexposure, so we're adjusting our camera systems for the future. I'll be focusing the next portion of my talk on Sleeping Bear Dunes and Good Harbor Reef, where we did a 10-kilometer transect, as an example of how we're summarizing the data and how we'll arrive at an estimate of total biomass for the lake. Good Harbor Reef is a shallow, heart-shaped reef in northeastern Lake Michigan. We sampled this location on August 24th. It was about a 10-kilometer sample. Took about 3.5 hours. The depth range we covered was from 3.75 to 26 meters. And when we take every 25th image, that led us to 3,450 images, 88% of which were usable, and of those, 25% had fish in them. We were able to identify a total of 3,317 fish, and we actually have latitude and longitudes for the positions of each of those along the transect. We've developed a method to size the fish, and you can look on the left side here. We tried a circle, we tried an ellipse, and eventually we landed on this method that can track the curved shape of a fish. And that essentially gives us the total length of each fish. When we plot those out, with the y-axis here is the number of fish, and the x-axis is the size of the fish, you can see a nice bell-shaped curve with a long tail. And you can also infer that around 70 millimeters was the average size of the round goby found on Good Harbor. When we portion those out into 5-meter depth bins, you can see we found the greatest abundance of fish here in the 10 to 15-meter bin, and that there's maybe some inference here that we're getting smaller fish at 15 to 20. And so we can look into those results later. Then when we make the conversion of length to weight, and then we divide that by the area of each image, we're able to plot the numeric density, which is the number of fish per meter squared, as well as the biomass density, which is grams wet weight per meter square. And you can see that there's a lot of low values here, that these are what we would call a skewed distribution. And the reason for that is that we had a lot of zeros. 75% of our photographs were zeros. But where we did have positive values, we can summarize the means in the bottom left here within these depth bins. So you can see we had the greatest mean density and mean biomass density in the 10 to 15 meter bin. And when we average those across all of these, you can see that the average was 0.65 fish per meter squared and 8.12 grams per meter squared. Now, we developed a method to extrapolate those per meter squared estimates out to total abundance using a measurement of the total area within the assessment area. So in this case, we're talking about Good Harbor Reef. It's a 10 square kilometer habitat. When we break that out into depth bins, and then we summarize the total area of those on the left-hand side here, you can see the total area in meters squared per depth bin. Then we have these densities, and then when we multiply area by numeric density or area by biomass density, we can get an estimate of the total number of fish per depth bin, as well as the total weight per bin. When you add those up across the entire reef in every depth bin, you can see we're estimating slightly over 7 million fish on Good Harbor Reef, and we're also estimating about 89,000 kilograms, which is 0.089 kilotons of fish just in that 10 square kilometer area. Now, when we move to the lake-wide scale, we'll also be considering coarse versus fine substrates. And so we'll be using a LiDAR elevation surface that's been published by NOAA. You can go to the NOAA lake level viewer here, shown on the bottom right, and you can infer the surface texture, essentially the roughness, and what types of features are on the bottom from this. We're hoping to use these data to infer coarse versus fine proportions in the 0 to 30 meter depth range in Lake Michigan to make a lake-wide extrapolation from all 30 transects, not just the one I just showed you. When we look at our results just from Sleeping Bear Dunes, a few things are obvious. First, even with just this 10 square kilometer area, we're already accounting for about 3% of the 5-year mean in our bottom trawl data, which is 5,300 times larger area approximately. Actually, it's probably a little less than that, but in general, the point is that we're already accounting for a large portion in a relatively small area with our new method. The other thing is when we compare our numeric densities with other published values in the Great Lakes, we find them to be within the range of other published values, perhaps a little bit on the lower side of that range. And the other point I'd like to make is that this estimate is likely to be conservative because we have imperfect detection of fish that are hiding under rocks, that are hiding in algae, that are too small to be seen given the resolution of our photographs. Now, so far we've been doing all of our labeling of fishes by hand. We've outsourced that to a company through a partner, but what we're doing is we're using the hand-labeled images to train computers to detect the shape and size and color of the gobies in images. And so far, we've been able to establish a method to put bounding boxes on gobies and assign probabilities to those. So for instance, here in the upper part of this image, there's a 88% probability that this is a round goby. And we're also working now to have the computer draw the polygon around each fish, essentially accelerate the whole production of this method. Currently, this algorithm, this automated process, is functioning with 82% accuracy. So looking forward, the first thing we're going to do is try to incorporate substrate into our assessment and come up with a lake-wide estimate of round goby. Then we'll be comparing that to our bottom trawl information and disseminating information to our partners. Next, we're basically improving and expanding our program. So first, we're building a second GobyBot 2, should come online in summer 2021. We're also redesigning our camera and lighting to improve our exposure across all depths, also expecting that this summer. Then we're hoping to expand from Lake Michigan into Lake Huron and eventually into Lake Ontario and Lake Erie in the out years, starting this summer in Michigan and Huron. And then we're continuing to develop our automation so that we can deliver this more efficiently in less time. With that, I'd like to acknowledge many funders and supporters, Great Lakes Restoration Initiative, U.S. Geological Survey, Environment Canada all provided funding for this work. There's been a number of people that have helped produce the survey, both field work and the analysis. The Fishery Commission and Council of Lake Commissions has generously provided time and input to this process, including the individuals mentioned here, in addition to Chris Lagarde and Jeff Tyson. And finally, we have Michigan Technological University and L3 Harris as some technology partners. With that, thank you very much for your time. Here's some of the references that I shared, and I look forward to the next phase of the discussion here. Have a great afternoon.